So this related rates question says that a weather balloon with a radius of 12 meters develops a leak, losing air at a rate of 24 pi meters cubed per minute. Find the rate of decrease of the radius after 4 minutes. Okay, so here we go. Once again, we're looking at a circle here, something that's spherical or circular here. Here's our radius. What do we know? Okay, well, what we're doing here, first of all, is we have some information about the volume. We know how fast the volume is changing here. So what we're doing is we know that the volume of a sphere is 4/3 pi r cubed. We know that. We know that the radius, okay, at least this thing starts at 12 meters. That's not exactly true later on in the problem, because we're going to see that the radius is changing here. So this is really just a starting point. Just make sure that we understand that that's starting here. We know that dV by dt is equal to 24 pi meters cubed per minute. And we would be smart to put a negative in here to identify or to indicate that this is decreasing. Okay? That this represents a decreasing rate, not an increasing rate. So we're subtracting volume, we're not adding volume here. Okay, what we want, oh sorry, and we're at the specific time here is 4 minutes. Whoops. 4 minutes later, okay? What we want is dr by dt. We don't know what that is, that's what we're looking for. Okay, well, first of all, we're going to start with this relationship here. We know, and I'll zoom in a little bit more. Whoops, wrong way. Okay, so we know that volume is equal to 4/3 pi r cubed. And we'll take the derivative of this, so dv, and we're doing this implicitly because time does not show up. Okay, whoops. Time does not show up as a factor here. So we take the derivative, and notice when we take the derivative of r cubed, it's going to require the chain rule. So we bring down the 3, r squared, and then we have to multiply by the derivative of r. Now, we're going to try to plug stuff in here. We know that the volume is changing. It's negative 24 pi meters cubed per minute. The 3's are going to cancel here, so this will be 4 pi. The radius squared. You know what? We don't know the radius squared at this point right here. Now we are looking for dr by dt, so eventually I'm going to solve for this here, but I don't know what the radius is after 4 minutes. So we got to do a little bit of work here. Okay, what is the radius? Okay, what is the radius after 4 minutes? Well, thing is, right off the bat here, we don't exactly know here. What we're told is how much volume we're losing. Well, is it possible to go from volume to radius? And the answer is yes. So what we're going to do here, we have to figure out what the initial volume was. So our initial volume, I'll make that VI, is going to be 4/3 pi, and our radius here started at 12, so 12 cubed. Okay, 4/3 pi times 12 cubed here. And actually, I'd probably be smart to at least simplify that in terms of pi. So 4 divided by 3 times 12 cubed. And this is going to be equal to 2,304 pi. That's our initial volume here. Now, we lose 24 pi meters cubed per minute. So in 4 minutes, we lose 4 times 24 pi meters cubed. Okay, or in other words, we lose 96 pi meters cubed. So the volume, the volume at the 4 minute mark, and maybe I'll put a little subscript 4 there. The volume at the 4 minute mark here is going to be that initial volume, 2,304 pi minus 96 pi. Okay, And so now that makes it actually pretty easy to work with here. So at 4 minutes, this is going to be 2,208 pi. Okay, well now we know the volume at the time that we're interested in. So it doesn't take us much to convert that actually into a radius here. So therefore we know that if volume is equal to 4/3 pi r cubed, then we can write 2,208 pi is equal to 4/3 pi r cubed. Don't forget to write the pi there. Okay, we did all these calculations in terms of pi. So that needs to be part of this calculation. If you forget to put that in there, then we've missed a significant portion of this. So the pi's will cancel. So we're going to multiply through by 3, divide by 4, which gets us 1,656 is equal to r cubed. And now take the cube root of that. Okay, that doesn't work out nicely there, but that's okay. So what I'm going to do is I'm just going to write this right now as the cube root of 1,656. This will be meters, and that's going to equal my r. Okay, good. So now I have the radius at the specific moment I'm interested in. And by the way, just so that you have an idea here, this means that this is approximately 11.8 meters. Roughly here. But I'm going to stick with this right now for the next couple seconds. So I know it's kind of weird. I went off to the side here just to do some work, but I'm going to come back now and I'm going to plug that number in. So this is going to end up being, need a little bit more room here. Okay, the radius that I needed here was the cube root of 1,656. That'll be squared. And that was multiplied by dr by dt. Now to get dr by dt, I'm just going to divide. And so we will get negative 24 pi over 4 pi times the cube root of 1656 squared. This is equal to dr by dt. Okay, well, the pi's will cancel and I can divide 24 by 4, so it'll be negative 6 over the cube root of 1,656 squared equals dr by dt. But you know what? That's probably not a huge benefit to us. That probably doesn't actually communicate what we'd like to see here. So I'm going to take this to the nearest tenth here. So negative 6 divided by that cube root of 1,656 squared. And we get, and I get here, negative 0.04 meters per minute is equal to dr by dt. All right, that's how fast the radius is changing. Okay, it makes sense. It's negative, so it means it's going down. I realize that's kind of small here. I mean, that means we're losing, is it just 4 centimeters? Okay, move that over 2 places here for the centimeters. It's only 4 centimeters per minute. 12 meters, though, you got to understand, is really big for a radius. I mean, that's an enormous balloon. So, yeah, that's reasonable. There's our answer.